Hi guys, welcome back to my channel. In today's video, I'll be discussing about the radiation from an ideal dipole. So guys, if you haven't seen this playlist radiating systems, I recommend you to watch the first video, which is the wave equation for the time retarded potentials, because some of the results I'll be using which I derived in this video. So let's get back to our video. So radiation due to an isotropic source. Now, what is an isotropic source? Isotropic source is a source which equally radiates in all directions. That is, it has the same electric field and magnetic field in all the directions. Now, to find the radiation due to an isotropic source, we just need to determine the electric fields and the magnetic fields as a function of the source current distributions. Now, let us first calculate the radiation due to a realistic source. That is, we'll take an ideal scenario, which is the ideal dipole, which is also called as an Hertzian dipole. So it is just a small current carrying wire of length L. Here the length L is very small as compared to the wavelength. Operate wavelength here, and the wavelength refers to the operating frequency. Now I'll be using this result of the vector magnetic potential which I derived in the earlier video. The playlist link I will keep in my description. You can find it. So this is the formula for the vector magnetic potential, and we know that R is mod R minus R dash, and V is the wave velocity in the present medium. So let us assume the current distribution to be typically of this form, and its direction is in the unit vector along the z-axis. So now the vector magnetic potential, when we simplify, we get the magnitude as this, and the direction will be the same. That is, it points towards the z-axis. That is the total magnetic field. We can write as the magnitude multiplied by the unit vector along the z-axis. Now, after finding the vector magnetic potential, we can easily find the electric field and the magnetic fields from these formulas. These formulas also you can check from my previous videos. Now to simplify this electric field and magnetic fields, we'll be using two properties. One is this vector identity, the formula which is given here, and another thing is I'll be using spherical coordinate systems, because as I said that in Cartesian coordinate systems the calculations becomes a little bit hectic. So I'll be using spherical coordinate systems where I can take advantage of the spherical symmetry. Now, if I evaluate this electric field and magnetic field under these conditions, so I'll arrive at these results. The magnetic field becomes this and the electric field becomes this. Now, typically there's the dipole, so it has generally three regions. One is the reactive region, and there is the near field region, the last one is the far field region. So the formula for the reactive region is the distance r, it is less than or equal to lambda by 2 pi, and for near field it is like greater than lambda by 2 pi and less than or equal to 2d square by lambda, and for far field the r is very much greater than 2d square by lambda, or sometimes people even refer to this formula where the r is very much greater than lambda by 2 pi. So if we impose this condition on these formulas get simplified to these results. So this is the electric field and the corresponding magnetic field. So now let's find the power radiated by an ideal dipole, which is given by the Poynting vector. And this is the formula for the Poynting vector, which is half real times E cross H conjugate. As you can see in the far zone, I'll show you a picture. So this is the picture of the near and far field of an Hertzian dipole. As you can see that for the far field, the fields are radially directed. So that is what I have written here. The fields are radially directed in the far zone. So this Poynting vector gets simplified to the magnitude of the electric field by 2 neta. Here neta refers to the intrinsic impedance, and its value is equal to 120 pi or 377 ohms in air. So now around this dipole, let us consider a sphere of radius r and then calculate the power radiating through that sphere. So the total radiated power is given by this formula. if we just evaluate this integral and do some basic maths, so we arrive at this result. This is the final radiated power in a far field region of an ideal dipole. So this shows that the radiated power is real and it is independent of R in this far field region and is just proportional to I naught L whole square, where I naught is the magnitude of the current and L is the length of this current. So this is the visualization of the Poynting vector distribution around an ideal dipole antenna. You can just see. Now I would like to discuss more about this far field conditions. So the far field, also known as the Fraunhofer region, as I said, the formula for this is the region where the distance r is greater than or equal to 2d square by lambda, where d is the maximum dimension of the source. So in as you can see that in this picture, this is the ideal dipole, this is the near field, and this is the far field. The near field also called as the transition region or the Fresnel zone, and the far field is also known as the Fraunhofer zone. So now let us typically see the radiation due to a half wave dipole. As you can see, guys, this is the picture of the half wave dipole. So for a resonant half wave dipole, we know that the length is lambda by 2. That is, this length is lambda by 4 and this length is lambda by 4. So the total length is lambda by 2. And let us assume the current distribution is typically of this form. Now, when we use the above equations, this equation and this equation, we first find the vector magnetic potential and then the electric field. We find that the electric field is directly proportional to cos of pi by 2 cos theta by sin theta. So this gives our electric field patterns of this half wave dipole. So when we plot this, we typically get a donut shaped radiation pattern of this half wave dipole antenna. So you can see in this picture, this is how the radiation pattern of a Hertzian dipole looks like. So in my next video, I'll be discussing about some antenna parameters. After that, let's do some simulations to see how these fields appear for a dipole, ideal dipole and a Hertzian dipole, and some other dipoles. Thank you so much guys for watching this video.